All right, just to review, this is section 5.4, I think it is, for normal distribution, foundations, math 20. So we were looking at normal distribution. So whenever we do normal distribution, we need to draw out our bell curve, right? In the middle, this will be our mean. And in this case, we have 1,000 cars were recorded by photo radar. The mean of 105 kilometers an hour. So 105 kilometers is the mean of their speeds with a deviation, standard deviation of 10 kilometers an hour. So when we have our normal distribution, we're going to go one deviation above, 2, 3, 4, and 1, 2, 3, 4 below. All right. So 100 with a deviation of 10. So the next one will be 115, 125, 135, 145, speeding, and then coming back the other way. So 95, 85, 75, and grandpa over here at 65 kilometers an hour. Yeah. So we want to know the number of cars traveling between 115 and 125. Well, that's this spot in here, right? So what we need to do is go look at, let's click on here, at our normal distribution graph, right? And we see that we get 34% in here, 34% in here, 13.5, 13.5, right? 2.35, and 0.15 in the end, all right? So go back to that one. All right. So we want to know the number of cars traveling between 115 and 125. Well, this was 13.5% in here between 115 and 125. So what do? Well, we take 1,000, because this time we want to find the number of cars, times 13.5%, and we get 135 cars that are traveling between 115 and 125. Yeah? Okay. So, as I said last time before the video crapped out on us, right, is that this standard or normal distribution for standard deviations works great when we're looking for cars between 115 and 125, or from 75 to 125. We just simply add up all those percentages that are always the same. Now, the problem is that what happens if we wanted to know how many cars, or even what percent of cars, there were from, let's say, 88 kilometers and 107 kilometers. Well, I don't know how far. I know that half of this is 50. I know the whole thing is 100, and I know how much each one of these deviations, because they're all the same, what the percents are. But I don't know how much it is to 88% from 107, because I don't know this little part in here, right? All I know is that this is 13.5% from here to here, but I don't know how far it is from here to here, or even from there to there, as far as that goes, right? So this is our next unit, or our next section, which is on Z-scores. The Z-scores will allow us to find those kinds of things, all right? Now, any questions about this?
No.
Okay. Pretty straightforward. So let's jump to this one, Z-scores. So this will be section 5.5. We'll just go back up to this one for a second. All right, so this you can find in your textbook. These amounts will always be the same. Right? So if you wanted practice questions, page 251, I think it is. 251. sounds right, yeah. 136. Oh, 136. So we do page 251, 1, 3, 6, 10,
13 and 15.
13, and 15. All right, so that'll give you some practice exercises. All right, so let's jump into our next page, which is 5.5, and let's look at Z-scores. All right, so Z-scores compare data in between those ranges on our normal distribution curve. It's a value that indicates the number of standard deviations of a data value above or below the mean. A normal distribution has a mean of 0 and a standard deviation of 1. So what that means is that on our little distribution graph, right, our mean is 0. Plus 1 deviation, minus 1 deviation, plus 2 deviations, minus 2 deviations. So it's standard: plus 1, plus 2, plus 3, plus 4. 4 above the mean, 4 below the mean. Okay? So when we want to find parts of those, we need to use Z-scores. All right, let's move this up. All right, and we'll jump to here. So, formula. In order to compare any different normal distribution curves, we have to standardize a normal distribution. We use Z-scores to do this. So our formula, Z is equal to X, that's our data point, minus the mean, right? Remember the symbol X with a little line on top? That was our symbol for mean, divided by the standard deviation, right? So record this formula so that you have it, and I'll give you a couple examples of what this looks like. We'll jump to the next page. Okay. So actually, let's go back to that for a minute. One thing I want to point out is, just like any operation, right? This is really Z over 1, right? It's a fraction, right? So because we have an equality, we can isolate by cross multiplication any of these variables. So if we want a definition for standard deviation, well, that's going to be our data point minus our mean divided by our Z-score, and that will tell us our standard deviation, right? If we want to know our mean, for example, all right, well, Z-score times the standard deviation is equal to X minus the mean, right? So what are we going to do? Well, we're going to bring this, either way, it doesn't matter which way we do it, but I'm going to bring this to this side. Okay. So this would be the standard deviation plus Z times the standard deviation, or Z times the standard deviation will equal X. So that will give us the term that we're looking for. If we have the term that we're looking for, all right, what we need to do then is get rid of, right, get rid of our X. So we could subtract an X from this side, subtract an X from the other side. So Z times standard deviation minus X equals negative the mean. So what I'm going to do? Well, we're going to divide everything by -1. So divide this side by -1, divide this side by -1, and we have a formula for finding the mean. Right? So we can cross multiply all these all day long. Right? So for every formula you have, you can isolate the variables just like any other equation. Does that make sense?
Yep.
All right. So let's look at an example. All right. Oh yeah. So this, by the way, I think how do they do this? Yeah, this is symbol. Yeah, this symbol here looks like a U. All right. This is what they sometimes use for standard deviation, or for the mean. Right. So I just simply replace that. Right. So if we want to find our Z-score, so here's our formula: X minus the mean divided by standard deviation. Well, we know that our term X, 36, minus our mean, 165, and our standard deviation is 48, right? So remember that when you have a fraction and you have to do equations in the fraction, you must figure out the stuff on the top first, and then the stuff from the bottom, and then do your division, right? So you have to do the each part separately. So 36 minus 165. What do you get? Negative 129. All over 48, right? So now, here's the thing about z-scores, is they are all percentages as expressed as a decimal. So we can just simply take a negative 129, divide it by 48, and we're going to do this to 4 decimal places. Actually, we're going to do it to 2 decimal places. Negative 2.69. So we get z equals negative 2.69. Yeah? Right? Alright, so notice that it's negative. So if I was to draw a normal distribution curve, right, where here's my mean, and here's 1 deviation above, here's 1 deviation below, here's 2 deviations below, there's 3 deviations below. Negative 2.69 is going to be somewhere in there, right? You know, close to 3, but,
Yeah.
right? All right. So, that's how we find our z-score. Well, big deal. What is that? How does that help me? Right? So, let's go to this next slide here. All right. And we're going to look at, we'll come back to this negative 2.69. So remember, sometimes you're going to get negative numbers, sometimes you're going to get positive numbers. So that just refers to whether it's above the mean or below the mean. Right? So let's click on this table to go. And this is also in the very back of your textbook. All right. Let's see if we can move this up a little bit. There we go. Okay, so they're giving you an example here. So some z-score tables are different, and you will always be provided with a z-score table. You don't have to memorize these numbers, okay? But there's a bit of a trick to understanding how they work. All right? So there's the one page that has all your negative numbers, and there's the one page that has all your positive numbers. But you have to look at how this is working. So in the example, they show you negative 1.15. That's 1 and a little bit more, 0.15, deviations below the mean. But you'll notice that the color, or the part that's shaded in here, is this part of our graph. So it measures from the left up to negative 1.15. Right? So there's a couple of different things that we can do here, or that we remember. So remember that the mean is always at the 50% mark. The whole thing is what? 100%, okay? So, if we know that this part here is, well, it tells me 12.51%, 0.51%, okay? Yeah. Then we could theoretically find out how far it is from here to here, or even from here to the end. Because this would be 100%, right? Minus this 12.51% would tell us what's in here. Or 50% minus this would tell me that little part in there, yeah? Right? So we can play around with the math here. So you have to be careful. How do you set this up? Well, in this table, it's always measuring from the left to that value, all right? So negative 1.15. So what we do is we first go to this side of the table, and we're going to have to move this up a little bit till we get to negative 1.1, because our number is negative 1.15. Negative 1.15, yeah? So we go to negative 1.1, because that's the first part of this decimal, right? And then we come across until we get to, bring this back down a little, Okay, oh, right there. Okay, to our 0.05. So 0.05, that takes me to negative 1.1, that's where we were. And then negative 1.1, and then the 0.05 part. So that gives me the negative 1.15. Does that make sense?
Yeah.
So what we do is we just simply go like this, and here we get this probability number, right? 0.1251. So let's just move that down a little. Yeah, there we go. So 0.1251. So it's always a 4 decimal number. Now this is a probability number. Probability is always from 0 to 1. 0, it doesn't happen. 1, 100% it happens, right? So probability, these probability numbers can easily be changed into a percent. How do we change any decimal number into a percent?
Like times it by 100.
Yeah, multiply by 100. So we simply multiply this by 100 and we get 12.51%, which is exactly what they tell you right here in the example. All right? So let's go back to our last page. Ooh, oh yeah, there we go. What did we have? Negative, no, we had, where's this, where's that one? Oh, right here. The z-score that we had. What was our z-score? Negative 2.69 or something?
Yeah.
Okay, so let's go back to our, back to our table. So go to this next slide, go to the table. Negative 2.69. So let's get you doing a little practice with that. Okay. So negative 2.6. There's negative 2.6. Now our next number, or our third digit is the 9. So we need to go to the 0.09 part, and we're just going to follow this along. All right? So we get 0.0036, right?
Yeah.
Which if we multiply that by 100, what do we get? 0.36%, right? So that negative z-score of negative 2.69, right? So remember our little picture here, right? Negative 1, negative 2, negative 3, right? Negative 4 over there. Deviations below 2.69, somewhere in there, right? But that means that from here, from here to this part is 0.36%, right? So that means that everything else from here to here will be 100% minus 0.36%. Right? I mean, it's a lot. A z-score of negative 2.69, not a lot of items in that area, right? And it shouldn't be, because remember that in our normal distribution we have 34%, 13.5, 2.31, 35 I think it is, and 0.15, something like that. Should add up to 50, right? So from here to here is 2.35%.
Right.
So up to 3 deviations, or from 4 to 3 is only 0.15%.
Right.
So we shouldn't have that much, yeah?
Yeah.
Okay. So let's close out. We will refer back to that, or you'll go to your textbook and look at it. All right? So I'll give you some practice using those. So let's go to determine the percent of data to the left of a z-score of 1.24. Okay, yeah, great. So let's go to our table, 1.24. So now we're on our positive, no we're not, let's go move this up. Okay, that's 1.24. So 1.2, and then we go over to 4.8925. Yeah, let's close that. 0.8925. Did you see that? You saw that? Everybody saw it? No. Okay, 0.8925. 0.8925. Now, that's not our answer, right? Well, it might be. It might be our answer. We have to be careful here. So here's our mean, right? Here's 1 deviation above. Here's 2 deviations above, 3, 4, right? 1, 2, 3, 4 below, right? So, remember our Z table measures from here up to 1.24. Oops, 24. Right? That's our Z score. So, if we want to know the percent of data to the left, well, from here to here is 0.8925. That's, how much is a percent? 0.25%. That is this part in here, right? So you got to be careful. The question said to the left of that. Well, to the left of that, yes, you're right, is 89.25%, right? Let's look at the next one, right? To the right of negative 2.35. So here's negative 1, there's negative 2, negative 3, negative 2.35% is going to be from here to here on our Z-score table, right?
Right.
What we want to know is to the right of that. Well, to the right of that would be from here to here, so that would be 100% minus this little part to give us the value to the right of that. Yeah, so we go to our Z-score table, negative 2.35, right? So negative 2.3, and I'm going to go over to 0.05, 0.0094. Okay, so 0.0094 or 0.94%, right? So that means to the right of that will be 100% minus this 0.94%, right? Which is going to be, I don't know, 99.06 or something?
Yeah.
So 99.06% will be to the right of a Z-score of negative 2.35.
Right.
Yeah?
Yep.
Now, why is this important? Remember our car example? How many cars? Well, we want to know how many cars are going faster than a Z-score of negative 2.35. That's this way. 99.06 times the 1,000 cars, right? Right. Okay, let's see. Do we need to get another one? What's this one? Next one. Oh yeah, there we go. Oh yeah, between. Let's try those. Yeah. So here's again. We got. You're gonna draw this this bell diagram, this graph, multiple times. Okay. So that's why mine look a little sloppy, because I keep drawing it over and over again, faster and faster. Right. So what I do is I always draw my little bell diagram. There's my mean. All right. So I want 1 above, 2 above, 3 above, 4 above, 1, 2, 3, 4 below. Yeah. So between there's negative 1, negative 2, negative 3, negative 4, right? Plus 1, plus 2, plus 3, plus 4, right? Deviations. So negative 2.88. That would be somewhere in here, right? And negative 1.47 would be somewhere in here. Agreed? Mm-hmm. Okay, so we're really dealing with this area in here. Yes? Mm-hmm. Okay.
Yeah.
So, here's the problem. We know how far it is from here to here. We know how far it is from here to here. Right? Or we even know from here to here is 50%. Right? We can look up how far it is from here to here. So what we're going to do is we're going to use our Z-score table and find out how far it is to negative 1.47, how far it is to negative 2.88, and then to find the distance between, well, what are we going to do? Subtract the shorter part from the longer part. Yeah, that's it. Right? So, you want to see what that is? 2.88 and 1.47. Let's go. So, negative 2.88 0.0. So I'm just going to change this into 0.20%, because it's 0.0028. And what was our other number?
1 point.
Do you have it written down? Negative 1.47. We hit the table. Let's go negative 1.47. So negative 1.4, and then over to 7.0708. So that would be 7.08%. All right, let's go back. Okay, so that means from here to here, 7.08%, and from here to here, 0.20%. So the data between, or the percent between negative 2.88 z-score and negative 1.47, 7.08% minus 0.20.
6.88.
6.88%. Yeah? Does that make sense? Okay. Any questions about that? Good. Let's look at this next example. All right. Oh yeah, good old IQ tests. Right? We're going to see how smart you are. No, I'm just kidding. So, but yes, IQ tests follow a normal distribution curve. All right, so here's how we do these kind of questions. So, IQ scores are normally distributed, and there's the key word, it's normally distributed. Well, normally distributed means that it follows this normal distribution curve, right? It's up, same on both sides, with a mean of 100, right? So most people, right, 100, that's the average, the mean, and a standard deviation of 15. Okay, well that means that from the mean of 100, 115, 130, 145, what's next?
55. 155.
And 15?
Oh, whoops. 160.
160, yeah, that's where I am.
No.
Okay? So, 100 minus 15?
185. I mean 85. Sorry.
85, yeah. Right? 70,
55.
55.
40.
Potato, yeah, 40.
Potato. Yeah.
Right? Yeah, if you have an IQ of 40, you're potato. Right? So, here's the thing. 34%. 34%. Right? So, this is one deviation below, one deviation above. So what does that mean? Really, it means that of the people that take an IQ test, right, their intellectual capacity, their intelligence quotient, is 68% of the people out there will be between 85 and 115. So not a bad score. Right? Now, there is going to be, what do we got? 13.5, 2.35, 0.15%, right? So yeah, Sheldon from the Big Bang Theory, right? Somewhere between 145 and 160%. 0.15% of the population going to be in that sort of genius level, right? Stephen Hawking, you know, I don't know, probably in there somewhere, right? Just like 0.15% are going to be below 40, right? Did I do that right? 13.5, 2.35, and 0.15. There we go, yeah. So 0.15% going to be below 40, yeah? Okay. So, if a person scores 119, so let's say this person here gets a score of 119, yeah? Well, how does their score compare to the general population? Well, there's a couple of ways that we can look at this, is that there's this many percent of people who scored below that person, right? Or there's this few many people, right? This few people over here, who scored higher than 119. 119 is a pretty good score, right? That's within one, right? And we know this is one deviation. We know this is 2 at 130. So we can anticipate some z-score of 1 point something, right? How do we find that z-score to find out what percent it is from here to here that scored lower than her? Well, remember our z-score? Z equals x minus the mean divided by standard deviation. Do we know our mean?
Wait, 100?
100. What's our deviation? 15. And we now have our term, our x of 119. We can find our z-score. So what are we going to do? Well, we're going to take 119 minus 100 divided by 15, and we get 19 divided by 15, which gives me, I don't know,
1.26 repeating.
1.27, we'll say. Right? That's our z-score. So our z is 1.27, and it's positive. Yeah? So what do? Let's go back to this one, so we can look at our table to go. Okay, 1.27. Let's move this up. 1.2, 1.2, positive, keep going. 1.2,
7.
and 7. 0.9147. So 0.9147. All right? So 91.47% of people scored below this person. Right? Or, if you want to look at it the other way, 100 minus 91.47, what does that give me? 0.3, so the 8.53% scored higher than her. Not a lot of people, right? Okay. So, z-scores, normal distribution are a way to compare data. Let's see, what's our next little thing here? We should probably move this up a little bit. Okay, that's the one we just did. Oh yeah, that's the next one. Next example. Oh yeah, sure. Oh yeah, so this is a good one for all those people that are out there running. Right? So athletes should replace their shoes before their shoes lose their ability to absorb shock. Yeah, because they want to protect their knees. Right? So running shoes lose their shock absorption after a mean distance of 640 kilometers with a deviation of 160 kilometers. So some will fail a little bit before, some will fail last a little bit longer, right? So here's our normal distribution curve with a mean of 640 and a standard deviation of 160. Right, so 640 and 160 should be 800. And another 160 would be 960, right? And going the other way, 640 minus 160. 480. And
320.
320, all right, and so on and so on and so on. Okay? So Zach is an elite runner, and he wants to replace his shoes at a distance when only 25% of the people would replace their shoes, right? So remember that this is our mean, so this is really 50% of the people, right? Yeah? He wants to find 25%, where 25% of the people would replace their shoes, okay? Well, 25% of the people, so that would be, I don't know, whatever it is, somewhere in here, right? 25% of the people, this way. Yeah? Before these people. So, let's pull this out so I don't have to keep drawing all this.
There
There we go. Okay. So wait. So 25%. So what we do is, oh yeah, okay, so, yeah, it might be easier to show you that, to show you on that chart. All right, let's back this up a little bit to our table on the go. Okay, okay, 25%. So at 25%, now because our chart doesn't deal with percents, it is a probability number, we have to change this back into a decimal number. So that means we have to divide by 100 instead of, right? So we get 0.2500, right? 4 places. Right? So what we're going to do is we're going to go up, pull this up here. Oh, not so far. Okay. So what we're looking for is 0.2500 on our chart. So just to help us figure that out a little bit, we know 25% is somewhere in the middle of our 50%, right? So I'm going to say it's probably somewhere around, let's see, 34% is from there to there. So 25, yeah, it's probably somewhere past at least one deviation to the left, right? Right. So I'm going to look in here somewhere for a 0.25 or as close to that as I can find it. So here's 0.22, here's a 0.2514, here's a 0.2483. Right? So in this area, 0.2483, 0.2514. Now here's the problem is there is no 0.2500. Right? So what we're going to do is we're going to take these two values, right? Well, actually these two z-scores, right? So what z-score would give me a value of 0.2483, this first one, right? Well, that's negative 0.6, and this number up here is, just pull up, 8, negative 6, 8. All right, and we're gonna move this down just a little bit. Oh, 0.2483 right there. Okay, and then negative 0.67 will be our 0.2514. Yeah. So, okay, let's get out of that. Okay, so that means that we average these two together, so negative 0.675, yeah? Right, add these two together, divide by 2, negative 0.675. This becomes our z-score, right? No, we're on the wrong page. We need this one here. Yeah. This one. There it is, okay? So, negative 0.675. So, when we have negative 0.675, 675, that's our z-score. Remember this formula? Right? Well, we knew that in that question, let's move this out of the way for a second. What was our standard deviation was 160 and 640. Okay, go back. 160 and 640. All right? So, here's our mean, 640. Here's our standard deviation. So, this is right over 1. So, what are we going to do? Well, we can cross multiply, right? Or you could isolate the term, add 100 to the other side. But either way. So we get negative 0.675 times 160, right, is equal to x minus 640, right? So then what we're going to do, we're going to add 640 on this side, and we're going to add 640 on this side after we do this multiplication, and we find out that x equals 532 kilometers. All right? So let's move this thing out of the way again. All right, so at what distance should he replace his shoes? 532 kilometers. Make sense? So there is some practical usefulness to this. As we can see, normal distribution. Okay. So, the main takeaways from this, we started off with our normal distribution curve, right? 34%, 13.5, 2.35, 0.15, okay? 100% of the data, right? 50% of the data, right? Notice that 99.7% of the people will be within 3 deviations, plus or minus, right? Very few people are going to be potato. Very few people are going to be Sheldon from the Big Bang Theory. Yeah? All right. Our Z-score, again, that will allow us to find intermediaries in the middle of, right? Make sense? Okay, questions for practice. You're going to do page 5.5. That would be questions page 264. Page 264. So on page 264, you will do questions 1A. I don't know what that is. You'll do question 6, 7, 8, 15 through 17, and question 21. Okay?
Right.
Okay, so there's one more section of this, which will be our next video. It's a real short section on confidence intervals. We'll see you on the next one.